Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We are at lecture 2.6, Memory Model and Locality, and we're going to be learning how to write a tiled matrix multiplication kernel. The objective of this lecture is for you to learn to write a tiled parallel matrix multiplication kernel. And we're going to write code to be able to load simple tiles for matrix multiplication, and we're going to learn how to use barrier synchronization correctly, and we're going to go over some resource constraints or considerations, and then for this particular lecture, we're going to assume that the m, n, and k, which are the matrix dimension values, are all multiples of the tile width for simplicity, and we will deal with arbitrary m, n, and k values in the next lecture. This slide shows a quick review of the concept of tile loading for our matrix multiplication. And we're going to have a very simple scheme where we divide up the strips of A and B that we need to use to compute the entire tile of C. And for each step, we're going to have a tile of A and tile of B that are the same size as the tile of C that is being computed by a thread block. So we're going to be able to calculate the address of the corresponding locations of the A element and B element in the tile as long as we set that location to be the same relative position as the C element that this particular thread is responsible for. So during loading, the thread is going to be responsible for a C element, an A element whose row index will always, or the Y dimension index will be always the same as the C element. And however, the X index, position index, will depend on the thread idx.x. So this gives us for the index calculation for A element in loading that blue tile. And it's really the Y index is row, and the X index is the thread idx.x. Now, when we look at the B element, the thread is responsible for the Y index, or the vertical direction index, is going to be determined by thread idx.y, but the horizontal index is going to be the same as the C element, which is COL. So this gives us the index calculation for loading tile 0. When we move to phase 1, we're going to load tile 1 of A and tile 1 of B. So if we look at the position of the blue dots that need to be loaded into the shared memory, we see that the Y position of the blue dot remains the same as the previous tile. However, the X position of the blue dot has advanced by a full tile width. Essentially, we're moving horizontally from the blue tile to the orange tile. So that's why the coordinate for the X dimension for that blue dot has advanced by a full tile width. And if we look at the B tile, it's the same situation, but in the Y direction. So the Y position of the blue dot has advanced by a full tile width. So that's why when we look at the index for the A element and B element, the A element is still going to have its Y index determined by row, but the X index is going to be tile width plus the thread index in the X dimension. And when we look at the B element, the Y index is going to be tile width plus thread index in the Y dimension, and the X index will remain the same as determined by column or COL variable. So this gives us a generalization of the teeth tile that we're going to be loading. The teeth tile is going to be the tiles that we're going to be loading for phase T. And we just showed T equal to 0 and T equal to 1 in the previous slides. So for the teeth tile, the A element that we're going to be loading will still remain, the Y index is still going to remain the same as the row variable. But for the X index, we're going to multiply tile width by T and add it to the thread index in the X dimension. For the B elements, we have a very similar calculation. The Y direction index is going to be calculated by T times the tile width plus the thread index in the Y dimension. And then the X index is going to remain the same as the C element, which is COL. So as long as we understand this calculation process, it will be very easy for us to write the code in the kernel to load A and B elements for into the shared memory by every thread. So now let's look at the source code. In the first part of the source code is still pretty much the same as the simple matrix multiplication kernel. So but here we already discussed the declaration of a tile shared memory array for A and the a tile's worth of shared memory array for B. So we call these ds underscore A and ds underscore B. ds means device shared memory. And the size of each array is tile width by tile width. So each array will be able to accommodate tile width squared number of elements. For a 16 by 16 tile, we'll have 256 elements in A and 256 elements in B. And we just define some abbreviation variables, bx, by, tx, ty, to give us shorter names for the for these variables when we use them in the tiled loop body. So with these abbreviations, we can calculate row and column, and this remains the same as the simple matrix multiplication. So every thread is going to just determine the row index and the column index. Essentially, it's the Y and X indices into the C array. So then we'll initialize the C value to 0 for every thread. And this is an automatic variable here. So every thread will have its own private C value variable. And that variable is going to be in the register. So now we're ready to look at the tiled matrix multiplication code. This is where the code is quite different from the basic matrix multiplication kernel. We will actually have an outer loop that iterates through the phases. So the loop at line 8 actually iterate over the phases. And so we're going to have T as the iteration variable that indicates which phase we're in. So we're going to start from phase 0, and then we're going to go all the way to n divided by the tile width. So this gives us the multiples of n, that n is relative to the tile width. So this gives us the total number of tiles. So we're going to iterate from 0 to the total number of tiles minus 1. And within each tile, or each phase, every thread is going to be responsible for loading 2 elements, one A element and one B element into the shared memory. So this is the code for loading the A element, and this is the code for loading the B element. The shared memory array is indexed by the thread index, thread index in the Y dimension, as well as the thread index in the X dimension. And if the index for A element and B element is exactly what we discussed in the previous slides. So as long as you understand the reasoning behind the calculation of these elements and a linearized them according to the row major layout. So you should be able to see exactly why we have the expression for A and B in these two loads. So even though we only see two statements, remember every thread is going to execute these two statements. So for a 16 by 16 tile size, we're going to have 256 threads. Each thread will be loading two elements. So this is how we can load the 256 A elements and 256 B elements both into the shared memory. And here we see a sync thread in line 11. This is important. Remember, all the threads will be loading these elements, but they may be loading these elements at different speed. So some of the threads may finish a lot earlier than the others. So sync thread is the barrier synchronization, as we discussed in one of the previous lectures, that allows all the threads to wait for each other until all the elements in those two tiles have been loaded into the shared memory. So once all the threads have reached the sync thread, the threads will proceed to calculate a segment of the dot product. And this is done by the for loop, where I is going to iterate from 0 to tile width -1. So every time we go into this for loop, we're only going to calculate a segment which is the same as the tile. The length is the same as the tile width. And so we're going to be accessing the elements from the shared memory for both A and B. And this is essentially, we're going to use ty to select the y position of the element in the shared memory, and then we're going to use the iteration variable to go through the x position for A, and we do the opposite for B, and this should all be illustrated with the example in one of the previous lectures. So all the threads will execute this for loop according to their own thread index and block in the x and y dimensions. And then we will do a synchronization, a barrier synchronization. This barrier synchronization allows all the threads to wait for each other and make sure that all the threads in that same thread block have completed this segment, their own segment of the dot product. So when all the threads have reached the synchronized sync thread, that means that everyone who needs to have to use any element in the shared memory tiles have completed their work. So this is the signal that we can begin to overwrite the contents of the tiles in the shared memory. So this brings us to the next iteration, where we will advance the t, which is the tile index, and then we will load the next batch of elements for those two tiles, and we will continue the process. So after we finish all the tiles, we will come out, and now we have all the C element values in the C value register variable in the threads. So all the threads will now write out their C values according to the row and column positions that are determined by their thread and block indices. So this writes the result into the final C outcome. So here we go. We have a simple parallel matrix multiplication algorithm using tile algorithm. And so let's take a look at a few important things and analyze it just a little bit. So each thread block will have quite a few threads. If we use tile width of 16, we'll have 16 by 16, which is 250 threads in the thread block. If we use tile width 32, we have 32 by 32 threads in the thread block. That gives 1,024 threads. So this is quite a lot of threads for the thread blocks. For tile size width of 16, each thread will perform 256 loads to A and 256 loads for B for the thread block. So these are all the loads that we need to do in order to load the tiles, the two tiles, 1A, 1B, into the shared memory for each phase of the execution. And once we loaded all these elements into the shared memory, we will be, remember, every thread is going to be doing a segment of the dot product, which is 16 multiplication and 16 add. So that gives us 2 to the 16 floating point operations. And we have 256 threads. So this gives us a total of 256 times 2 times 16, which equals 8,192 floating point operations. So now we are seeing that for every 512 floating point loads from the global memory, we will perform 8,192 floating point operations. And in the simple matrix multiplication case, for every floating point operand we load, we are doing only one multiply add. So here, the ratio is actually improved by 16 times. So as you can expect, for 32, the ratio will be improved by 32 times. And we show the calculation here. I would like to encourage you to repeat what I did for 16 so that you can fully understand the calculation involved in understanding the ratio between the global memory loads and the floating point operations that you can perform based on those loads. So let's look at some resource considerations for using shared memory and threading. So let's say, as it turns out, the hardware streaming multiprocessor in the Fermi GPU can be configured to be either 16K or 48K bytes, depending on how large you want the L1 cache to be. So the combinations are 16K byte shared memory and 48K byte of L1 cache, or 48K bytes of shared memory and 16 byte of L1 cache. Both add up to 64K bytes. There are two ways of dividing this storage between shared memory and L1 cache. So for simplicity, let's assume 16K bytes for some of the calculations, and you can repeat the calculation for 48K byte as a homework. So one of the important things to remember is that shared memory size is implementation dependent, and we're going to come back to this point before the end of the lecture. And second one is for tile size of 16, each thread block uses 256 elements in each tile, 16 by 16. So each tile has 256 elements. We need to load two tiles. So we need to have 2 times 256 elements. And every element has 4 bytes. So this gives us a total of 2K bytes, or 2048 bytes. So every thread block will require 2K bytes of shared memory storage just to be able to accommodate the A tile and the B tile. And since if we had used the 16K shared memory configuration, this allows us to have up to 8 thread blocks executing at the same time in the SM, in the streaming multiprocessor. So this gives us the potential of up to, remember, for every phase, each thread block will have 512 memory loads to load all the elements of the two A and B tiles. So if we have 8 of those blocks, we can have up to 8 times 256 times 2, which is 496 loads that can be, all simultaneously active at the same time. And this gives us plenty of opportunities to do zero-cost scheduling among the warps, so that if some of the loads come back earlier than others, we can run those warps to make progress and so on. So this gives us a lot of flexibility in terms of scheduling these thread blocks and warps that are associated with these thread blocks to tolerate memory access latency. So the next tile width will be 32. And this will require the use of 32 by 32 tiles, and that gives us 1,024. We need to have A and B, so that gives us 2 of them, so the 248. And then each element is 4 bytes. So this gives us a total of 8 bytes, 8K bytes of shared memory usage per thread block. And so for 16K byte shared memory, this would give us up to 2 thread blocks. But there's a catch here. Remember, in the Fermi streaming multiprocessor, we can only accommodate up to 1,536 threads in the SM. So we actually will have exceeded the thread limit if we use 2 of those thread blocks for the 32 by 32 tile configuration, because we will have 1,024 threads in each thread block, and having 2 of them will exceed the 1,536 limit. So this is a good example of the interactions of resource limits. Each resource limit gives you a certain limitation on the number of threads that you will have running your kernel for your configuration. And the resource constraint that has the most strict limit will dominate and determine the final runtime activities that you can have in the hardware. So in this case, the thread capacity limitation of the streaming multiprocessors will prevail and limit the number of thread blocks to be only 1 if we use the 32 by 32 tiles. Going back, so this tells us that the 16 by 16 tiles is probably a better choice regardless of the shared memory size. That is, even if we increase the shared memory size to a bigger size, we would not have been able to run more of the thread blocks in the SM anyway. So assuming the 16 by 16 tile size, we actually reduce the number of global memory accesses by a factor of 16. And you should go back to the 4 by 4 matrix example in the previous lectures, and the 2 by 2 tiles, where we already gone over the details, and you saw that for a 2 by 2 thread block tile, we reduce the global memory access by a factor of 2. So here we use 16 by 16, we reduce the global memory access by a factor of 16. So let's do a very simple calculation. For Fermi, we have 150 gigabytes per second memory bandwidth. So that means that we can have 150 divided by 4, giga operands per second. And remember, for every memory operand that we load in the tile algorithm, we will be able to perform 16 floating point operations. So this gives us the maximal floating point operation we can support, potentially achieve with this tiled algorithm. It's 150 divided by 4 multiplied by 16, which is 600 gigaflops. And this is much, much closer to the 1 teraflop peak number that the Fermi GPU is designed for. So this is the reason why it's so important to use tiled algorithms for calculation like like matrix multiplication. So one final comment of caution again is that each synchronization, barrier synchronization or sync thread call can potentially reduce the number of active threads for a block. So that's why it's very important to be able to have multiple blocks all running in the same SM. Some of them may be doing barrier synchronization, some of them are not doing barrier synchronization, so that we can more fully utilize all the execution resources in the SM. So this is another reason why we need to be careful not to go over to get to too big a tile, because when we use a bigger and bigger tile, we'll be having smaller and smaller number of blocks that can be running simultaneously in an SM. So let's now go back to one of the previous comments I made about the device, the size of the shared memory being a design choice, or it depends on the particular generation of hardware that you're using. So in order for the CUDA program to be able to adapt to different generations of devices, CUDA provides a device query API function. And you can ask about the number of devices in your system by calling CUDA get device count function. And then you need to supply an integer variable, and you need to supply the pointer to that integer so that the function can return the total number of CUDA devices in your system. Most of you would discover that when you have a computer, you can easily have more than one CUDA device in the system. You could have a very small GPU in the chipset. It can have a discrete GPU in the system for the real compute. So this will give you the total number of GPUs that are designed to support CUDA in your system. And then you can actually query the capability of each device by going through a for loop that goes through all the devices from device number from 0 to the device count by -1. And then for each device number, you can call a API function called CUDA get device properties. And this, you need to give it a variable that is declared of type CUDA device prop. And this variable is actually a structure variable. And you pass the pointer to that variable into this function call. And when this API function returns, you will deposit all the properties of the device of this number to you. And then you can use a piece of code right after the return of the function to determine if the device has the right amount of resources and capabilities for your use. So in this case, you probably want to pick the discrete GPU that has the computation power that you would like to use, rather than the small GPU that may have come in your chipset in the system. And so when you look at the properties, you should look at the CUDA user guide for all the fields that are returned in the CUDA device property variable. But the two most relevant ones up to this point in our class is the fields of the max thread per block property. Remember, some of the earlier devices only allow up to 512 threads in a thread block. And Fermi GPU and beyond now allow up to 1,024 threads in a thread block. So having, looking at this number would tell you which generation of GPU that you're actually using, and you can tell the maximum number of threads you can have in each thread block. So a lot of the CUDA programs use this to adapt the configuration, the kernel launch configuration, to make sure that they stay within the allowed limit of the particular device that they're running with. And the other one that will be useful is the shared memory per block field. And this gives you the total amount of shared memory that you can use for each thread block. So this also a limit that you should try to respect, so that you can always run your code within the limit that is set by the hardware. So this brings us to the conclusion of lecture 2.6. And I would like to encourage you to read the textbook, entire chapter 5, if you'd like to learn more about tiled algorithms and the tiled matrix multiplication algorithm, and then how we can implement that algorithm in CUDA code. Thank you.